All right, I think I covered this already, but let me just make sure. So this is approximately where I was at the last video. So it says the crystallization of chemical sediments from water solution, low solubility of minerals precipitate first because. All right, so let's think about that. All right, so low solubility means it's difficult to dissolve those minerals. All right. Um, because they're more easily, dissolved more easily. Nope, that's definitely not it. Because they're more susceptible to being dissolved. No, because that's pretty much the same as being easy to dissolve. They are not easily dissolved. That sounds like the right answer. They are infinitely soluble. I don't even know what that means. All right, so yeah, it's C. They are not easily dissolved. All right, that's why they form. Um, all right, so let's move on. All right, so I think this is actually where I stopped last time. So there are three general types of rocks. Igneous rocks are formed. Well, they're formed in two different ways. They're formed by within the earth, by cooling magma, or when magma reaches the surface of the earth, it's called lava. So when the lava cools at the surface of the earth, you can also form igneous rocks. All right, we'll get into that in more depth. So there's also sedimentary rocks, and sedimentary rocks are you already have rocks that are subjected to weathering or erosion. For example, like you think about like some boulder that's just been sitting there for billions of years, and it rains on the boulder and the water freezes, and when water freezes, it expands, and so maybe little pieces of that boulder start to crack off, to break into these sedimentary rocks. Or so there's those little pieces will get buried, and we'll get into that, like exactly how that forms. Basically, there's like a cementing process that goes on. And it's actually fairly easy to identify. I mean, that's the big thing, is how do you identify the difference between igneous rocks, sedimentary rocks, and metamorphic rocks? All right, so metamorphic rocks form from pre-existing rocks, and they transform by heat and pressure, or you can actually have chemical fluids. Usually, we're talking about water. With some chemicals in it. All right, so we're going to go into depth in each of these. We'll start with igneous rock, and then and we'll end with metamorphic. The one thing I should say, and I'll probably repeat this, is that metamorphic rock, you're changing forms. That literally was what this means. You're not melting the rock, right? If you can't turn it. You can't turn these pre-existing rocks into magma. Once you do that, you've changed it into magma. It might become a rock again. That's fine, but that's not metamorphosis. That's not metamorphic rock. Metamorphic rock, you heat it, but you're not heating it, or you're not push. You don't have enough pressure and heat to turn it back into magma. Okay, so I mean, it can come close, but the moment it turns back into magma, that is not metamorphic rock anymore. It's just magma, and like I said, it might turn back into igneous rock. All right, so let's start with igneous, right? And actually, that's kind of leading towards what's going to be called what we call the rock cycle, right? So rocks can go through this cycle. We'll do that at the very end of the chapter. All right, anyhow, igneous rocks are formed by the cooling and crystallization of magma. Magma, if it's deep inside the earth, or lava, if it's at the surface of the earth. All right. All right, and so So rocks that are formed within the Earth are called plutonic. Um, Another name for plutonic is also intrusive. So it can either be called intrusive or plutonic, as long as these rocks were formed from magma inside of the Earth. All right. So if it's formed outside from the lava that you usually from a volcano or a fissure somewhere on the Earth, that's called extrusive. Right. So intrusive inside of the Earth, extrusive outside of the Earth. All right, let's go back to our slides, see if I can do this without pausing. All right, so, all right, here we go. All right, so, yeah, so those are the two main ones. Let's see. So igneous rocks is generated through basically magma. If it's in the Earth, and of course, it's called lava. When the magma reaches the surface, temperatures increase within the Earth. Like, so, if you start at the surface of the Earth and you start to dig down, this is the average rate. The temperature increases. So this is what they call a geothermal gradient. So the temperature increases roughly, and it's not exactly this much, but roughly on average about 30 degrees per kilometer. So you go down so many kilometers, and each kilometer you go down, the temperature rises, right? Because you're getting, I mean, it's a long ways to get to the core, but you're getting closer and closer to the core of our planet, which is extremely hot. Now, we can't dig. There's no way we're not even close to digging, even into the mantle of the Earth, which is, another. That's about 3,000 kilometers from the from the crust to the mantle, or going all the way through the mantle. So we're not anywhere near that. But that's what happens is here. Let's take a quick look at a picture of that. Here, I think I have it already open. Not there. Let's see, where is that? Is that right here? Oh, right. Nope. Sorry, I thought I had it open. Oh, there it is. Here, I gotta move this over just a little bit. Well, it's not gonna let me move because I'm already recording. But this picture over here, so this is just showing you that it's not quite a straight line, but on average, the temperature increases by about 30 degrees Celsius per kilometer. All right, so that's the little the gradient, and you can see somewhere just below about 35 kilometers, you could start melting rock. All right, so that's something to keep in mind. But below this, just to let you know, that's where it could start melting, but it doesn't. Right? Not always. I mean, like you might think, at 30 kilometers and below, everything is molten rock. And that's not the case, right? The mantle is not molten rock. And the reason is pressure, right? It's here, let's go back to this. The pressure actually keeps the mantle from turning into molten rock, right? Or turning into magma. It'll just keep it in a kind of, like, you can almost think of it as a really thick plastic. I mean, there's a little bit of malleability to it, but it's still considered solid. All right, let's go to the next one. So in this particular case, about the heat is really a minor player. All right. So the role of pressure reduces. Reduced pressure will lower the melting point. That's a really important point. Is that when you reduce the pressure, the melting point of the rock will lower. That's really important to get that. All right. When the pressure drops, the what's called decompression melting will occur. All right. So for example, like if you have a pressure cooker, that's a good way to think of it. Or you think about the inside of the earth. Or so before we talk about the pressure cooker, you think about like the inside of the earth, right? There's an inner core. So there's an outer core, and then inside of it there's an inner core of the earth, made mostly of iron and nickel. But the inner core is actually solid, and that's just because of the tremendous amounts of pressure. However, on the outer core of the earth, it's iron and nickel as well, but it's actually liquid. Right? And we'll get more into why we know that. For a pressure cooker, what's going on there, of course, is you seal the water in, and so the water vapor doesn't have a chance to escape. So that's increasing the pressure, of course. Within the earth, we're talking about what happens when you decrease the pressure. If you open up the lid of the pressure cooker, right, the temperature will begin to go down. All right. So this is actually the thing that's really affects how igneous rocks are formed. The big player anyway is fluid, and really it's just water that we're talking about. There's always like anywhere from like 1 to about 5%, maybe a little bit more, 8%, up to 8% of the magma material. This actually has water in it. Just as a little side note, that was actually one of the big surprises when in the late 1960s, when the Apollo astronauts brought rocks back from the moon. They were rocks that were very similar to the rocks on Earth. In fact, they brought back some basalt, which is we find at the bottom of our oceans, but it didn't have any water in it, like no water at all. And it was extremely dry rocks from the moon, and so that was actually a big revelation that we didn't know that's the way the moon rocks were going to be. All right, so here's what happens. Like for example, when you add salt to water, like for example, you have an icy road and you add salt to it. I mean, people do this in the wintertime. Governments do this, and what that does is it lowers the melting. It lowers it lowers the temperature at which ice can form, right? So the ice will begin to melt. Just you didn't heat it up or anything. You just added salt, and the salt has lowered the temperature by which ice is going to form. Ice will still form if you get down to low enough temperatures, but it drops pretty dramatic, pretty substantially. All right, so even though the temperature at depths is hotter than rock's melting point, the rocks at that depth are solid because, I just mentioned this, they're under enormous pressure. There's an increase in pressure that prevents the melting, and the temperature would have to be even higher to counteract the increase in pressure. Actually, all of these are absolutely true, right? So D would be the correct answer, and there it is, of course. All right, so here, let's look at the next one. All right, igneous rocks. So we have generations. Generation of magma. All right, so how, The melting of rock into magma occurs over a broad rate. That's important, actually. It doesn't happen with at one particular